Okay, so we've got the fundamental idea of quantum mechanics, that all matter is actually probability waves and the wavelength is given by the de Broglie relation. Let's see if we can use that to actually work out the properties of matter. I will start off with the most fundamental property of matter of all, which is the size of an atom. Now, our basic idea of an atom is that you have a proton in the middle and the electron, which is a fuzzy sort of probability wave around it. The proton is also a fuzzy probability wave, but because protons have larger masses, they have more momentum and therefore shorter wavelengths. So relatively speaking, the proton's in a small space. Now here we're just looking at a hydrogen atom, the simplest possible, with just one proton and one electron. But the answers we get in the method is very similar for other things. Now our basic idea is that the electron is trapped inside the atom. We'll call that some sort of size A. Because of its attraction towards the proton, it's so attracted to the proton, because of course the electron has a negative charge and the proton has a positive charge, and opposite charges attract. So the electron would like to get really nice and close to that proton, and if it was a particle it could. But it's a wave, and its wavelength, like anything trapped in a box, is going to be, roughly speaking, the size of the box it's trapped in. Now you can argue about exactly how we define the size A. Are we defining it as a radius or a diameter? And is that a wavelength or half the wavelength? But those are all factors of 2 and they don't matter. This is ninja physics. So roughly speaking, we'll say we've got an electron whose wavelength is about the size of the atom. Now, why can't it get smaller? If the atom is smaller, the electron will be closer to the proton, which the electron will like because it's close to that opposite charge. On the other hand, because the wavelength is shorter, its energy is going to be higher because of the de Broglie relation. So what we're really looking at is the interplay between these two effects. On one hand, the electron would like to squish in close because that will the electrostatics work in its favour. On the other hand, if it squishes in too close, it's going to have a very short wavelength and therefore a very large momentum, which is not going to help it settle down. Now, how do we balance these things? Well, let's, as usual in Ninja, use an energy approach. We look at the energy associated with squishing in close to the proton and the energy to do with a small wavelength. So let's start off with the energy to do with the small wavelength. Now, kinetic energy. We're going to do this classically and ignore relativity for the moment. It makes some difference in some cases, but it's for ninja purposes this is quite good enough. So kinetic energy is half mv squared. We know what the mass for an electron is, but what's its velocity? Well, we know its wavelength, and we know from the de Broglie relationship that the momentum is equal to Planck's constant over the wavelength, which is equal to Planck's constant over A, in this case because we're assuming the wavelength is roughly equal to the size of an atom because it's trapped in the atom. And we also know that classically momentum equals mass times velocity. So the velocity is going to be, roughly speaking, the momentum divided by the mass. So it's going to be, roughly speaking, h over am. So plug that in over here, and we find that the kinetic energy of the electron trapped in the space is going to be half m h over am squared, which is going to be, roughly speaking, h squared over 2m a squared. So that's, roughly speaking, the amount of energy associated with its momentum. It's got momentum, it's moving around. Quite what it means to move around when you're trapped in an atom is a bit obscure, but it must have momentum. Now let's look at the electrostatic energy. Now, electrostatic potential energy you can get by integrating Coulomb's law. It's like the potential energy of two charges at some distance apart from each other is equal to minus the charge of the first particle, the charge of the second one, over 4 pi epsilon naught, it's permittivity of free space, times the distance between them. So you get that by integrating Coulomb's law, which we'll cover elsewhere in the course. Now in this case, both the charges are the same. They're both E, the charge of an electron and the charge of a proton, is opposite to each other. So that's going to be, roughly speaking, E squared over 4 pi epsilon naught A. It's got a minus sign because we normally define potential energy as being 0 to infinity. As things get closer and closer together, the potential energy gets more and more negative. That's because if you did drop an electron in towards a proton, as it moves closer and closer, the attraction will make it go faster and faster. Its kinetic energy will be going up, and that must be coming from the potential energy. So the potential energy must be going down. That's why we have a minus sign here. So what we get is that the total energy is, roughly speaking, h squared over 2ma squared from up here, minus E squared over 4 pi epsilon naught A. So if you have an atom of size A, a hydrogen atom of size A, that's what its energy of the electron should be. Now let's have a look at what this graph actually looks like. Always good practice to try and understand your graphs. So we've got the energy, and we've got A, the size of the atom. Now we've got two terms here. Now this one is negative and goes as 1 over A. This one is positive and goes as 1 over A squared. So when you're a long way out, this one's going to get really small because it goes as 1 over A squared. As you make A bigger and bigger, this will eventually get really, really small. This one also drops as you go further up, but doesn't drop as fast because it's only got a single power of A at the bottom. So what that means is when you're at very large distances out, this term is going to dominate. And that's basically going to be a minus some constant over A. So it's going to look something like this. Minus 1 over A if it was just this term in the equation. How about this term? Well, because it's got 1 over A squared, when A becomes very small, 1 over something very small squared becomes very, very large. So this term is going to dominate when you're at very small values of A. That's positive, so it's going to look something like this. And when you add those two together, you're going to end up with something that looks like this at small scales and like this one at large scales. So that's, roughly speaking, the curve that we'd expect for the energy as a function of the size of an atom. And you can see there's going to be a minimum point somewhere. This minimum point is going to be the position of least energy. If you're out here, your energy is higher because you're further away and the electron would like to be close to the lovely positive charge of the proton. In here, your energy is high because the electron's trapped into an incredibly small place. It's battering around frantically with lots of kinetic energy to try and get out. Down here is the happy medium when the two balance out and you've got the minimum energy state. So you'd expect this value here to be about the typical size of an atom. And what is that size? Well, this is a normal problem in calculus. We've got this curve. We want to find the minimum. If you want to find the minimum of any curve, what you do is you differentiate to find the gradient, and then you set that equal to 0. Because when the gradient is 0, you're at a maximum or a minimum. And we can tell by eyeballing the plot there's only going to be one flat point, which is going to be over here. So let's differentiate that. So we get dE by dA equals, this is got an a to the minus 2. So if we differentiate that, it's going to give you minus a to the minus 3. So it's going to give you minus h squared over ma cubed. And this term's minus a to the minus 1. So that's going to give you minus 1a to the minus 2. Which minus minus is a plus. It comes out as e squared over 4 pi epsilon naught a squared, and we'll set that equal to 0 to find our minimum. And if you rearrange that, we find that the minimum occurs at a equals 4 pi epsilon naught h squared over me squared. If you plug the numbers in, that comes out as about 0.5 by 10 to the minus 10 of a meter. As you may know, the actual size of atoms is about 10 to the minus 10 of a meter, which is pretty close for that. Only a factor of 2 or so, which for Ninja is irrelevant. So we've correctly deduced from fundamental quantum mechanics how big atoms should be. They should be about 10 to the minus 10 of a meter, which is 0.1 nanometers in size. Pretty amazing, really.